The entire executable is encrypted with an XOR cipher. What do we do? Well, let's toss it into Ghidra's emulator. Okay, so here's the deal. We've been asked to reverse engineer this program called Payload. It does nothing when we run it, but in the background, it is calling back to someone else's Kali machine, and they have an open shell. Yet, when we throw it into Ghidra, we are greeted with a bad instruction message and a do while loop that performs an XOR throughout the entire executable. We're blind. We have a few options though. One option is to create our own Python script that will go through the XOR executable for us, or you can use a debugger, like Ghidra's emulator. At the end, this is what we want to see. To do this, I will be using VirtualBox, Kali Linux, and Ghidra. And as with most things in life, this all started off with a tweet. Craig Young has posted yet another excellent blog post. The blog post is called Unpacking Shellcode with Ghidra, and this video will be following along really closely with that blog post, so go ahead and check it out. Unlike in my previous videos, this time I will be using Kali Linux as my development environment. This will allow me to use Ghidra and create the payload using MSF Venom for testing. And of course, I will be using the Ghidra software reverse engineering suite, namely the emulator portion of it. But hey, if all this is a bit new to you, then take a few minutes to check out my first Ghidra emulator video where I slowed a bit down and took my time with it. Or you can try your luck with some Crack Me challenges. I love making videos on malware analysis and reverse engineering. If you have learned something, anything from my videos, or if you like the cool glasses that I wore at the very beginning, let me know about it. Click those magic YouTube buttons and strike up a conversation with me in the chat below. But hey, enough talking. Let's get hacking. It all started off with a tweet. Craig Young put out this tweet about his new blog post on medium.com called Unpacking Shellcode with Ghidra Emulator. So if you look through this blog post, you're going to see that we're pretty much following it down to the letter. A few things have changed, but pretty much we're doing exactly what Craig has put in this blog post, to include creating our own payload using MSF Venom on Kali Linux. You can also click here and you can get the payload without installing Kali or messing around with MSF Venom. We're going to make our own. So go ahead and check out his blog post. Alright, so I'm going to quickly go through all this, but because this is not a Kali Linux tutorial. Hey, if you want to see a Kali Linux tutorial, go ahead and subscribe, click the like button, and let me know down in the comments that you want to see a Kali Linux tutorial. But as for me, we're just going to breeze through this really fast. Something to pay attention to is that we're going to be running it as a shell reverse TCP. So we're going to want to make sure our MSF console matches up with that. So, alright, it has been saved as payload. I already had one there, so just overrid it. Too easy. And then we're going to jump into MSF console. And I'm just going to be copying and pasting these commands over because, once again, not a Kali Linux tutorial. Because what we're trying to do is just get an idea of what this does. So as we're reverse engineering it, you can get an idea of what to look for. We're not completely in the blind this time since we're still practicing it. Alright, now that we got the reverse handler going, we're going to go ahead and chmod the payload and then launch the payload. And this is what it is supposed to do. After a couple seconds, it will come in and it will make that connection, and then we'll have a reverse shell in the background. So I can ask who am I, it says Kali. I can ask the host name, and it says Kali as well. Then I can exit out of that. There we go. And then it was running in the background. As soon as I exited, it closed. So what we can also do is we can do this to a remote computer. So let's go ahead and log into here. And I got payload on the desktop, so I'm going to go ahead and run it. and it did absolutely nothing because Kali Linux wasn't ready for it. So I went ahead and jumped over to Kali Linux, made sure that it is ready. I went ahead and typed in exploit in the MSF console. We're going to run payload again, and then we'll jump over to Kali Linux, see what happens. And we're going to wait for a couple seconds, but there it is. So we can do another who am I. It's dev this time. The host name should be something different than Kali. It's Ghidra. And what I can also do is I can echo I can echo something onto their desktop. Alright, so we echoed pond onto their desktop. Let's see if it actually took. And there it is, right where we thought it would be. Subsequently, what we could also do is we could remove pwnd.txt, cover our traces, right? If you look, it is gone. So we are all right. I'm going to hit exit down here, and it's going to close out of the terminal. Is going to close that shell connection in between the two. So now that we've got an idea of what this payload is looking like, we're now going to use Ghidra. We're going to jump into it, and we're going to start dissecting it. And the way that I'm going to do that is by double-clicking on the Ghidra shortcut that I put on my desktop. I have a symbolic link on my desktop. You might not. Jump in the terminal, find your Ghidra, let's launch it. Alright, I'm going to go File, New Project, and I'm going to name it Unpack because, well, that's what we're doing. We're unpacking the shellcode out of this. I'm going to take this payload, drop it right in there. It is x64 architecture, little Indian, 64-bit architecture, default, 64-byte architecture, default, and compiled in GCC. Looks good. Alright, and then I like to do my static analysis in this CodeBrowser first, even before I jump into the emulator. And when I bring it up, I notice that in true fashion, it doesn't pop up automatically. So I'm going to go ahead and click open, bring it up again. Sometimes it does it, sometimes it doesn't. I noticed that it doesn't pop up automatically a lot more when you're using Linux machines. Alright, so here it is. It seems to be analyzed, and it seems to be analyzed well. But let's go ahead and take a look at some things. Let's look at the imports. There are 0 imports here. Let's look at the exports. We have entry. For functions, we have just entry. No labels, no classes, no namespaces. Something isn't quite seeming right about this executable. So let's jump into entry, in which we're already there. And we can look through here. We see we got a couple things being transferred from one register to another, and then all of a sudden, just bytes at the end. Nothing really else of any good substance. Let's look at the decompile portion. Oh, we got a lot of bad instructions, a lot of halt bad datas. And then here we have this XOR that is stuck in a do loop. So this is where we start to see that the entire executable is XOR'd, and when this launches, it launches that do loop that goes through and XORs it again, thus decrypting it or de-encoding it so that we can read it. By we, I mean the program itself during runtime. Right now, static analysis, we can't do much of anything. So let's go ahead and take it into the emulator. I'm going to close out of the CodeBrowser, and then let's launch the emulator. Alright, same thing. It doesn't pop up automatically. No issues. We're just going to open it right back up. And then I got my symbol tree over here. If you don't see the symbol tree, click back and forth down here at the bottom. Get your symbol tree, and let's find the entry point. And then I'm currently selected dynamic. I put all my stuff in the middle right here. And I made it really big text so you can see it. But I got my listings, my dynamic, and my decompiler. My decompiler looks just the same as before. And I'm going to go ahead and dive into this just a little bit more. What we see here is we have this right here that is 10. If we look here, middle click, we'll see it highlight with a couple other different places. So it's a do loop, and for every do loop, it decrements it by 1. And while it is not 0, keep doing what you're doing. So this is a counter. I'm going to hit L on my keyboard. I'm going to rename it counter. And then this one, it just points to entry. So this is a pointer char for variable 1 of entry. So I'm just going to rename this, pressing L on my keyboard, as entry pointer, so I get an idea of what I'm looking at. So for every loop, we look at the ulong. Ulong in that case is casting whatever comes after it as an address. So the address of entry pointer plus 27 equals the address of entry pointer plus 27 XOR'd. Okay, and then a ulong is 8 bytes in this case. So let's go ahead and take a look at what 27 is. So what I want to do is I want to see where this XORing is to begin and where it starts going every 8 bytes to do that XOR. So I'm going to bring up a calculator. Alright, I'm just going to use the Kali Mate calculator. Alright, and it is already in programmer mode for me. And then I want to keep it right there. Let's jump back over here. Let's go to listings. Let's find out where the entry point is. I'm going to click on entry. It's going to highlight this entire thing. And I see that my entry point is going to be 004-00078. Alright, that is the entry point. And then what it did is it added 27 to it. So I'm going to do that as well. Plus 27. And that gives me 40009 Foxtrot. So I'm going to jump back into my listing. I'm going to look down here for 40009 Fox. This is where it begins. If we scroll down, we'll see that there's a couple more instructions down here, followed by just a bunch of bytes written out. I want to go ahead and jump back to the decompiler. Now this might be the same for you, it might be a little bit different. It's a little bit different for me than it was on the blog post posted by Craig, but as I'm looking here, when I highlighted this 4009 Fox, it also highlighted right around here. Everything here at the unknown byte 10, the concat 62, the int 6, the param 1, that very well could be code that actually does something, but it doesn't quite match what is written above it. It doesn't quite match the code. It doesn't have any rhyme or reason. So there's a chance that this may also just be randomized XOR code that just so happened to match a couple different functions inside of the program, in which they would all be de-XOR'd upon launch. So we're going to pretend that all this is pretty much just the same as everything here in the green. It's just random bytes. And when we XOR them, they should all be XOR'd to something that is legible. So we're going to go ahead and do that. So even though I've got 9 Fox here highlighted, what I want to do is I want to start our emulating process at the entry point. If you run this a couple times and things just aren't working, go back and make sure that you have the entry highlighted and that the cursor is here before you hit the emulate button. So I'm going to hit the emulate button. There's emulate button at the top, or you can right click and go emulate program and new trace. Once you do that, you're going to see that everything populates. You can come over to the right side of your screen behind my picture. I have a modules icon and also have a registers icon, breakpoint icon. Go ahead and bring up registers, and we'll be looking at that throughout the time. But we do know that it is now being emulated, and we want to de-XOR everything at that 9 Fox point. So let's go ahead and see if we can find that again. I got 4009 Fox. Now that we're here, we're going to add a breakpoint. You can right click and click add breakpoint, set breakpoint right here with the software execute, or on your keyboard hit K. We'll make sure the address is correct with the length of 1 with SW execute. Let's go ahead and put that there. And now, what I would expect to see, don't hit run just yet. Let's go ahead and jump into the dynamic listing and see what it is. Right now, there's nothing there because the program has not run up to that point just yet. But what we are expecting is to see everything here to be ran and XOR'd all the way up to this function of 9 Fox, and it's to be dynamically put in a readable state here in the dynamic tab. So now that we have that set, double check that the blue dot is there along with the cursor, and now we can hit run. All right, it should very quickly flash up to the entry and then very quickly go back to where your breakpoint is. If you take your time and hover above this, it will tell you exactly, that the breakpoint is there and the cursor is there and the register is there. Let's go and check dynamic, and hey, there we go. We have it all. So we can look through this and go, line by line and try to figure everything out while in here, or we can save it and do our own analysis on that executable itself. And that is exactly what we're going to do. So we're going to highlight everything starting from 9fox all the way down here to this last syscall. If you look or hover, it'll actually say syscall. So that's what we're going to highlight. So since I'm already down here at syscall, I'm going to go ahead and click on syscall once, go up here to my 9fox, hold shift, and then click. It's going to highlight it all. Right click. Let's go to extract and import. All right, we are going to have it as raw binary. And for language, we're going to try to make it as close to the payload as possible. So we're going to click on that, and I'm just going to go ahead and do a filter search for GCC. And hit enter. And we've got a decent amount of options here. Starting off at the very top, AVR8. I don't want that. I don't want anything of those. As I scroll down, I see x86 with a variance default, size of 64, Little Indian, GCC. That's what I'm going to choose. That's what the payload was at first. So this is what we're going to make our output. So let's go ahead and click OK. And I did say that we're going to name an output. You can keep it as payload segment 0004009fox. I'm going to call it output. All right. So click on that. And once you do that, not only does it save it to the project, it brings it up and it's ready to analyze it and start rocking and rolling. So let's go and click yes, let it do its analytical thing. All right, and then hit OK. All right, so now we're ready to take a look at it. And the better way to do that is to hit the D button to bring it back into a decompiled mode, and then we can click on the decompiler and take a look at it in a little bit more familiar format. So if we see, we have 1, 2, 3, 4 syscalls, and then we have some bad data, but this is a lot more readable than it was earlier. So as for unpacking the shellcode, here it is. You have your 4 syscalls. Mission complete. But what do these syscalls do? So lucky us, in the blog, Greg goes through another step. And we're going to go ahead and do those steps right now to see if we can actually narrow down exactly what these syscalls do. So we're going to go up to this little green circle with a play button, and it's called Display Script Manager. You can also get into it by clicking into the windows and then going down the Script Manager. So what we're going to do is we are going to search for something called syscalls plural script. All right, if you do that, once again, syscalls script, calls is plural, and you'll see that we have this one right here. I have 2. I have already made a correction to it, but we're going to go into the original one. We're going to go ahead and run that one as is. And when we do that, we see that this script is intended for x86 or x64 Linux files. This is an extract of the Linux file. When we looked at it, it didn't have any of the ELF headers. There's nothing that says this is an ELF 64-bit file. We extracted it straight from there with none of the header information. So it has no idea that it's a Linux file, but we know it is. So we're going to go ahead and right up here, it says edit script with basic editor. Subsequently, you can right click, edit with basic editor. I'm going to enlarge this. All right, and then I am going to go ahead and change the text. We're going to make it bigger because we want to be able to see this. All right, if we were to scroll down and scroll down and scroll down, we're going to see this override, this public void run. It's right after all of the comments. Because what we're looking for is this portion right here that says, if the current program executable format is an ELF, and if it is equal to x86, run it. But if it's not, then we need to pop up this script. or this error message. So we want it to run regardless. So we can either take away that, which would really screw us up in the future, or for now we can just go ahead and comment it out. So we're going to use the /* there, and then the */ to symbolize that this is the part we want to be commented out. We're going to go ahead and save as, and I am going to name it no elf resolve x86 x64. So I'm just going to add no elf in front of there. Alright, and it has been automatically added. So just to make sure that it's there, I see it there, but I'm going to go ahead and do a search for no elf. There we go. Alright, so let's go ahead and run this. Double click. And we get no system calls found. Or I got no system calls found. If you went ahead and ran the script as is, and you were able to get some system calls, then that's awesome. So what you would be able to see is a lot of system calls that actually are written out as system calls. Mine are currently just saying system calls, and when I click into the decompiler, they still say system calls. So no dice for me. But you could make a Python script just like the one that we use that goes through everything that says system calls and figure out exactly what parameters pass before the system call is performed to get an idea of what it is. Well, we just want to do it real quick and dirty to get an idea of what this does. So we're going to do it the old school way. We're going to use Google, baby. And this is how we're going to do it. So let's take a real quick look at our listings. Let's scroll up and we see that at the very top we have something being pushed to the RAX. And then we have a system call. The way that you do system calls in Linux assembly is you push a system call that you want to be called into the RAX registry, and then you call syscall. So we're doing a syscall on whatever hex of 29 is. If we scroll down, we'll see that we have another syscall here, in which they are popping in the RAX after they've pushed the 2A. So hex of 2 alpha is going into RAX and then syscall, so we're doing a syscall of that. Subsequently with the other 2. So we have a grand total of 4. So this is how we're going to do it using Google. So when I did my research, I found a couple different websites that had all of the Linux syscalls, but I decided that I was going to settle on this one right here. This is the website that I found that seems to have the most accurate and most reliable information. So earlier we looked at these 4 syscalls, and I pointed out that this one has an RAX of 29, and then that is pushed into the syscall, and then it runs that. So when we take a look at the internet, this syscall of 29 correlates to this right here, which is going to be socket. So this first one is going to be socket. That's the first syscall that's called. The second one, we saw earlier, it had an RAX of 2 alpha. And 2 alpha is going to correlate with this one right here, which is going to be connect. So 2 alpha is going to be connect. This one is relatively easy. We got 21 pushing to the RAX, and that 21, that hex of 21 is going to be for dupe 2. So we're going to go ahead and put that in there. And then last but not least, I'm guessing you've already guessed what the fourth one is going to be. The fourth one is going to have RAX of 3 Bravo pushed into that syscall, which makes 3 Bravo. It's a little bit further down on this list, but it is the executable. So what we do is in Decode, we get a socket up and running, and then we connect to that socket. We duplicate the file descriptor, and then we execute a code. And if we really wanted to go further into this, we could see that the first parameter here is RAX. And that is the type of syscall that we want to do. The second one is RID, and which for this case of the exec one would be the file name. So if we really wanted to, we could follow the RDI and see that we have the RSP that is put into the RDI here. Then we could follow that RSP back. We could actually go back and figure out exactly what file is being launched. But the big thing is that after everything that we've done, we've finally been able to determine that this executable that was once encrypted with an XOR cipher, we can now say that it does a socket. It connects to that socket, it duplicates the file director, the file descriptor, and then it executes. Hey, we did it. We started off with being blind, and now we can see clearly, thanks to Ghidra Emulator and Craig Young's blog post. Thank you for hanging out with me and unpacking some shellcode. And a major shout out to Craig Young, who makes easy to follow tutorials. So go ahead and share what you learned with the world. And by pressing that like button, it will expand this video's reach. And feel free to check out the other videos on my YouTube channel and reach out to me if you have any questions. But until next time, keep reversing.